Team T.E.S.T.
We are in the city of Eindhoven, the city of light. So it's not a surprise that the team from Eindhoven, Team T.E.S.T, is also working on a light-based biosensor. Oh. So it may not seem like it, but this biosensor includes a light switch mechanism, and I'll talk through why that is. So the underlying phenomenon of our technique is FRET, First-Order Resonant Energy Transfer. And this is a transfer of a donor fluorophore to an acceptor fluorophore when they are close to each other without the emission of a photon. So let's visualize this. So we have this light, in our case a laser, and they are always exciting the donors. And when the acceptors come close to the donor, we see that the acceptors will receive this energy from the donor and they will emit wavelengths as well. If the distance is higher between the fluorophores, they will emit less. And what we want to measure is the FRET ratio. And if the acceptor emission is going up, the FRET ratio is also going up. So let's apply this to our molecular construct. So we start off with an antibody, labeled with these donors again. And attached to it is a protein in order to attach the DNA scaffold to the antibody. And what we see at the end of the DNA scaffold are two things. So we have this acceptor fluorophore, which is close to the donor, so it's emitting wavelengths. And that is because of creatinine acid. And creatinine acid is our analog to creatinine, and it has an affinity to the antibody. Therefore, in a default state, creatinine acid will attach to the antibody, and you already see that it's closed. But in the presence of creatinine, the switch will open. And that is because creatinine has a higher affinity to the antibody than creatinine acid. So creatinine acid will get displaced by creatinine, and you see that the distance between acceptor and donor will increase. So the FRET ratio will be lower. So we have a signal inversely proportional to the concentration of creatinine, which we can see here. So an increase of concentration of creatinine results in a decrease of FRET ratio. But what are the specifics of our molecular construct? So we've used the novelly discovered protein M, which attaches itself to the Fab fragment of the antibody. And our team have done mutagenesis on the protein M in order for it to attach DNA to it. And then we have the DNA scaffold. And it includes both single and double-strand DNA. It has been fully designed by our team, and it's designed in such a way that there is a good balance between stability, but also flexibility, so that the switch can open, but also close. And at the end of the DNA scaffold, we see this creatinine acid, fully synthesized by our team. And it's been made in such a way that the affinity is lower than that of creatinine, so that the switch can close and open. So we have the construct. We immobilize it to the substrate, and we put it in a flow cell. And we want to analyze this flow cell. So we are putting it on a sample stage. And we know that in order for FRET to happen, we need light. So let there be light. This is the laser we are using. And what we then get are both the donor and the acceptor signals. And we want to measure them separately so that we can calculate the FRET ratio. So here you see them both. And we're using two filters. So first off, we're looking at the donor signal. So we are using the donor filter. Then we use our filter slide to move to the acceptor filter. And we get the acceptor signal. And these are both captured by the camera. And the camera can be used by the user through an interface. So the video is acquired. And then we are going to calculate the FRET ratio. So we are capturing the donor signal, then capturing the acceptor signal, calculating the FRET ratio, and then determining the concentration of creatinine. And that's what we want. So in conclusion, what we have created is a unique assay, fully created from scratch. And that is because we have used protein M, we have designed the DNA scaffold fully, and we have synthesized creatinine acid. And it's worth noting that our method is easy generalizable. Swapping out the antibody and the analog, we can use our method for other biomarkers as well. And in our method, we are determining the creatinine concentration based on FRET, using our optical readout method. And by using this light-based biosensor, we hope to have made the City of Light proud. Thank you.
Yeah, thanks very much. On the FRET assay, how do you detect? Are you relying on detecting single antibodies?
We are using, as you can see, it's hard to see with the lighting, but we are grabbing a larger field of view, so looking at multiple events.
But at the single antibody
Yes.
level? Yeah, okay. And then how do you replace the creatine? So, I mean, do you have that in competition against...
Yes, we have this competition with creatine acid. So in the default state, the creatine acid attaches to the antibody.
no, go back.
Yeah.
Okay, so the creatine always replaces it. And how is this then reversible? How do you get rid of the creatine again, if you want to have a continuous readout?
Yeah, so we are using a flow cell, and we are flowing through a bigger volume than what was original in there. So all the creatinine that was in the flow cell will be like flushed out by adding a bigger volume.
Of what?
Of a new sample. So in the competition, we added like there is room for 20 microliters in the flow cell. And in the competition, we flow through 100 microliters of a new sample. So all the old creatinine which was in the flow cell will be flushed out. Or is that not what you mean?
Don't know. I'll give one.
I can just rephrase that maybe a little bit. These antibodies have very strong binding affinity, and you're already having something that is binding to it less. So I'm assuming that the binding with creatinine is very strong. And so when you flow the sample through the creatinine, there's no reason to unbind. And so that's the question. Will it unbind, and why, and how long does that take?
The exact biology specifics, that's for her. But we have tested the carryover effect, and we see that there is none. Well, it's not great. I cannot show you the graph, but the carryover effect is not significant.
Also, the antibody is quite low affinity for both creatinine and creatine acid. It's not that strong that it can't be attached anymore.
We picked the antibody based on we tried multiple antibodies, and we picked them based on lower affinity, so a higher dissociation rate, so that it binds, but it does within a few short time dissociate.
Okay, so yeah, so let me come to the front. So indeed, if the antibody has a too high affinity for the creatinine, it won't dissociate in time. But because we tried multiple antibodies and we tested where the carryover effect would be the lowest, and by choosing antibodies that don't have a too high affinity for both the creatinine and the creatine acid, so the analog, it dissociates a lot easier. And then with the pressure of the flow coming through it, it does dissociate in time for the new sample to come in. So the old creatinine does flow out of the sample.
Okay, so I ask the next question. So I see a lot, and your team can be proud. Yeah, so a lot development on this biomolecular switch, and you also have in the results document you characterize this very nicely. Yeah, but we have seen other teams. You know, they all talk about wearables and continuous monitoring and putting something on a patient. This is now a completely different thing you developed. You developed a desktop tool, right?
Yes.
So it sits on the desktop and you
our
test it.
business case is not based on a wearable.
Okay.
So maybe Danny can explain this a bit better.
Yeah, to not go into too much depth for the market potential, we are using it for the preservation of kidneys, for kidneys to be transplanted. So it's a desktop device, yes.
They are also continuous monitoring is needed.
Yes, they are.
Okay.
Well, currently no, but that's what we are bringing to the market.
Not. Okay.
Yeah.
Okay. Good. What did the experts say? Would
I'm
it
sorry?
be? What did the experts say? Would it be good to have continuous monitoring?
Yeah, for
the
the
transplants?
nephrologists we talked to, they thought it was a good idea.
Okay.
Thank you very much for your talk. Again, very impressive. I have a question regarding your actual essays you have done, because you showed the principle in detail. So how far have you been able to push it? Like, did you try to do any like calibration, concentration, and so on, or it stopped somewhere halfway? Because, you know, when I see the molecular construct, it's something what is unbelievably complex. Okay, I cannot imagine how you put it all together and made it work. But what about the essays?
Yes, so we tried different concentrations for the assay complex itself, and to see like the effect was on the sensitivity of creatinine. And also we tried different methods to attach it in certain ways. We had some problems with clustering of the antibodies. So that's what we tried to solve, and we have been able to minimize it by improving the protocols and adding, I don't know if you know it, but tween 20, that's something that makes sure that the donors are not attaching to each other. So that's how we try to improve the assay in such a way that we can measure in a certain sensitivity range.
Okay, thank you very much.
And can I add something to that? Because the clustering did give some problems with the signal, so that's why we had to minimize it, because then the donors are very concentrated, of course. But next to adding tween 20 and magnesium to make sure that the DNA parts can attach together, we tried attaching all the DNA parts, because there are 4 in the scaffold, step by step, and then adding the protein and the antibody. But we have confirmed that all the separate parts, so the analog, the creatinine acid to the DNA, and also the protein to the DNA and the donors on the antibody, all those separate parts definitely work. We have tested them with gels and stuff like that. And then while assembling it, we eventually went over to assembling most of the scaffold first to make sure that that is very well hybridized, and attaching the protein M with the antibody first to prevent the clustering more.
So I just quickly shoot. Yeah, so your method you developed looks to me very sensitive. So it's much lower limit of detection than what we have seen from the other teams. Is that right? So the concentrations are in the sub-micromolar. Huh? So is this really needed, or would you need to dilute, or what is the practical application then later on? So I just see, calibration curve with 4 data points. So I don't know, did you check for limit of detection and saturation of the sensor and so on?
At the when making the TRD document, there are 4 data points, but yeah, we have looked at higher concentrations, lower concentrations, and see what happened for the result. What we would like to do in the future is play around with the concentration of the construct so that we have better sensitivity results. But for now, the practical applicability is good enough for now.
Being more sensitive is always good.
Yeah.
Short question. So you said fully creative from scratch. It was from your point. So which part do you exactly mean? Because this interesting essay has been published before you. And also I want to just a little bit explain about how you synthesize this complex structure. Thank you.
Yes, so the antibody was commercially bought, but in the paper, like I think you mean the Tom So paper where this was published in, the DNA scaffold is attached to the antibody. However, we chose to attach it to the protein M because we attach it with a cysteine-specific conjugation. And on the antibody, there are multiple cysteines, so you don't have complete control over where the scaffold will be. So in some of the assays, it will be on a different place than where you expect it. However, on the protein M, there's only 1 cysteine. So you know exactly where it is every time. Also, what we did, the protein M is already like a novel protein, but the cysteine that was on the protein was first on the top, so here. But that would mean that the scaffold would need to make like 360-degree angle. So through 2 mutagenesis, we removed it here and placed the cysteine at the bottom. So the scaffold had a more wide range to make the angle.
And did you do these synthesizes yourself?
Yes. Yeah.
And also for the scaffolds, we decided ourselves which pieces we would need based on all the parts that we want on it. So we want the acceptor die on it, we want the analog on it, we want something to attach to the protein, and we need something to attach the biotin to immobilize it to the surface. So those are 4 parts. And we just played around a lot with sequences, and for every part we made sure that there was enough to hybridize so that it was stable in the attachment, but there was enough single-stranded as well for the flexibility, as Danny mentioned earlier. So with programs like the IDT oligo analyzer and NUPAC, we played around with the sequences to see which ones would attach nicely but still form the least secondary structure, so that the hybridization that would take place would be nice.
Good job.
Thanks.
All right, I think given the time, please raise an applause for Team T.E.S.T.